All right, transient conduction. Let's see where we were since last time. Okay. Here we go. Okay, so we already talked plenty about transients without conduction, and that is lumped capacitance. And then we talked plenty about gradients in steady state, and that was the concept of thermal resistance and dimensionless heat transfer, shape factor. Now this week we're putting the two things together, and we went through analyzing a sphere intuitively, just to develop a sense of what's going on, acknowledging that these things are actually quite complex. So we're doing as well as we can. I'm going to quickly quickly revisit here the effect of Biot number on this case a wall. And what we see is, let's see. Okay. And what we see here in is that if the Biot number is small, which is the case of lumped capacitance, in this case in which we are cooling down a wall, we would start at a uniform temperature, and inside the wall, the temperature is going to decrease all the way to the temperature of the fluid eventually. But as it cools down, the temperature is more or less uniform. Is it exactly uniform? No, it's not exact. And we have a formula to calculate it. The gradients inside are proportional to Biot. So a small Biot number means small gradients. Conversely, if the Biot number is huge, that means the gradients are huge, and the surface temperature on the wall or a sphere or whatever else would be, this becomes very similar to the temperature of the fluid outside. That is because at high Biot numbers, the convection coefficient is very high. It's a very intense cooling or heating on the surface, and the surface very quickly takes the temperature of the fluid, even if the center of the component, walls, spheres, or cylinders, still has not realized that there is a different action on the surface. So in this case, we would see that the wall that was at an originally uniform temperature starts to cool down, but does not cool down uniformly. First, it cools down very quickly on the surface to a temperature similar to the temperature of the fluid, and the center starts to cool down only after a while. We saw that. Now, we said, okay, all that is intuitive. Let's try to make engineering calculations with it. And if we make engineering calculations, we can assume a number of things. For example, for the case of a wall, that is the focus of these calculations here, we're going to assume is 1D heat conduction, is 1D in space, but is transient. And we can assume constant thermal conductivity, and we can assume no heat generation. And we end up with this equation that isn't innocent looking, but is anything but innocent. This equation is the same equation you write for pretty much everything. It all depends on the boundary conditions and the geometry of the body. So in this equation, we would have two independent variables, space and time, and space is 1D. So we're happy. If it was 3D, it would be X, Y, Z, and T. Those are heavy things. We don't want those right now. One dimension in space, one and time. The dependent variable is only one, that is temperature. That depends on X and time, position and time. For this reason, we know that we need that is, this equation is second order in X, first order in time. We already discussed that we need then two boundary conditions in X, one initial condition in time. We wrote them down here. We also looked into something that is the number of parameters. We have a parameter here that is alpha. X, time, and temperature can change for the same problem at different times and different places. But the thermal diffusivity never changes, right? Same with the initial temperature. That's a number that is good for the whole problem. And if I go over this, I can see L here. I can see H, I can see K. All those are parameters of our problem. And if we wanted to understand this, and we had these many parameters and these many variables, we would have the choice of, say, doing an experiment in which we say, okay, what is the effect of thermal diffusivity? We can do, say, 10 experiments and see. What is the effect of initial temperature? We can do 10 experiments and see. And if we want to do like a factorial matrix, right there we would have 100 experiments to do. It gets interesting. What is the effect of wall thickness? Let's do 10 experiments. Now we would have 1,000 experiments. Oh, what is the effect of thermal conductivity? What if the wall is made of styrofoam or is made of aluminum? All right, let's make 10 more experiments. We're at 10,000 experiments. You get the point. This would take forever. If you want to understand this by brute force of doing experiments, it would never end. And that is even assuming that your experiments are good, which not always experiments are good, right? The experiments can be very complex and unreliable. Wow. So do I want to do, if we have 9 magnitudes, 10 to the 9, 1 billion experiments? Here's where this dimensional analysis comes to the rescue. Dimensional analysis helps us reduce the number of experiments and increase our understanding. This Buckingham theorem that you were exposed to in fluid mechanics, I don't know the demonstration and doesn't even matter, but it says this: if we have 9 magnitudes, and these 9 magnitudes have 4 independent units, and one of those units is a temperature that is always measured in Celsius, right? That with an arbitrary origin, then we would have 9 minus 5, 9 minus 4 minus 1, resulting in a total of 4 in the dimensionless groups. It just works. It's amazing. So we went from having 9 magnitudes to having only 4 magnitudes. But it's even more interesting because of those 4 magnitudes, 3 magnitudes are variables. We have now a dimensionless space, dimensionless time, and dimensionless temperature. I still need 1 more dimensionless magnitude, according to Buckingham's theorem, and we can choose anything. The book, and I agree, chooses B odd, the B odd number. Now, our problem, if we look at rewritten, that is as far as we went a little bit further. If we look at the problem rewritten, the equation of heat diffusion in dimensionless terms is this. That is a universal equation for any material in any size. That's amazing. And here we have the boundary conditions that became fairly square now, right? Is 1. And this derivative, let's look at the condition of symmetry, 0 here, 1 here. And this one, that is a condition of convection on the surface, is the most difficult one. You used to have this very complex expression we see here, became this other expression here that looks a lot simpler. There is no simplification whatsoever in having gotten to this point. But look at this. Our problem is still it has one dependent variable that is theta, that corresponds to temperature. That theta depends on two independent variables, that is x star and t star, that correspond to space and time as before. But the problem before had, how many was it? Six, how was it? Six parameters. Now we have only one parameter, that is the B-odd number. Here we have B-odd number. If I want to see the effect of B-odd, I do 10 experiments, and the effect of B-odd captures the effect of all other parameters together. It's so amazing that now we could save so much money in experiments. But in addition, the equations we're gonna get are like so packed, so tight now that all I need to know is B-odd, and I can understand any wall of any size with any made of any material with any cooling or heating fluid around it. Extremely powerful, extremely powerful. If you think some people would, in my field, welding, you have the steel specialist, you have the aluminum specialist, you have the nickel specialist. They don't talk to each other, and they know so much of their stuff and so little of the other. But us, in heat transfer, we don't have steel specialists, we don't have aluminum specialists, we don't have brake specialists. A wall is a wall, and every wall is captured in this equation. Heat transfer has been around for 300 years, welding for 100 years. No wonder we're behind. And you can imagine the type of research I do. I'm trying to bring this into the world of welding. And it's having amazing results. If any of you wants to know, I invite you to come along. Okay, so now that we have packed this, every wall of every material with surrounded by any fluid, we have packed into a universal equation. If we solve that equation, we solve the equation forever. That equation is not too difficult. It's actually within the things that you were taught in math, but we will not worry about that. I'm gonna use the solutions that some poor person had to do at some point in order to get a PhD. And the solution is this one. And this, that might seem convoluted, remember, every time you use this formula, you are using 4 years of somebody else's time. So if you complain about all these symbols, just think could be so much worse. We could be either solving this or back to the Stone Age in which we knew nothing. This is the value we bring here. So it says the dimensionless temperature is this Fourier series. And this Fourier series depends on the variable T star, that is our dimensionless time, our X star, that is a dimensionless space, and these two coefficients, Cn and zeta n. Zeta n, Cn depends on zeta n directly. So I need to get zeta n, and zeta n depends on B-odd. So if you give me B-odd, I give you this zeta n, and I will get Cn, and I have the whole solution. All I need is B-odd, and I will tell you for every part of the wall at any time what the temperature is gonna be. That's amazing. That's so this is as far as we made it last time. I'm going to do today, we're gonna use these solutions. But here we have the plain wall. Now, let's move on to the cylinder. Now, for the cylinder, we would need to use the equation of heat diffusion in cylindrical coordinates. Now we're moving up. This solution, I think you could not do because it involves Bessel functions. Bessel functions are similar to sines and cosines, but they come typically from cylindrical symmetries. I used to teach this back in Argentina. We don't need to worry about that. The expression looks very much the same as before. We have a Cn, we have a zeta n, and this J0, J0 is one of the Bessel functions. It looks somewhat like a cosine function. It's like a damped cosine function. But whatever it is, the beauty is that you go to Excel and you can calculate it. It is in Excel. It's not in most scientific calculators don't have the Bessel functions, but Excel does. You can go and graph it and check it yourself. J0 looks much like a cosine that is damped with time as it goes. And J1, it looks much like a sine that is damped as it goes. So depends on, in this case, R star, that is the dimensionless radius, T star, that is a dimensionless time. And these coefficients, just as before, they have different formulas, but the working is exactly the same. You give me the Biot number, and I'm going to give you everything else. Much like before, this zeta n, they come from an implicit equation. You see, if I give you a zeta n, it's easy to calculate Biot. But the problem typically works the other way around. I give you the Biot, and the question is, what is this zeta n? These solutions are tabulated. In the book, you have a list of tabulated solutions. But wait, because things get better. Not only, okay, let me tell you about the sphere in a second. A sphere is much of the same story. Another Fourier series, and I'm not gonna get into details of this because eventually it's gonna be plug and chug. But we have a Fourier series here that depends on Cn and zeta n, and zeta n, Cn depends on zeta n itself. And guess what? It all comes from an implicit equation on Biot. So if you write one of these equations, you have gained 4 years of life right there. So if you write enough of these equations, you're gonna live forever, I guess. But this better, because this is only the beginning of the beauty. Because under some conditions, these equations are even simpler. What are the conditions? If the dimensionless time, remember T star is a formal way of writing it. Some people call it the Fourier number. In the book, you're gonna see it listed as Fourier. If this number is bigger than 0.2, give or take, again, nothing happens exactly at 0.2, but if Fourier number is bigger than 0.2, the series is determined essentially by the first term, because the second, third, and fourth term are so small that they don't matter anymore. This is awesome. Look, for the case of a wall, if Fourier is bigger than 0.2, the whole series solution becomes this expression I have here, C1, not Cn anymore, C1, exponential of zeta 1, not zeta n, not just 1, times T star and a cosine. Same for the cylinder and same for the sphere. Fantastic. Now, we still need to know what C1 is and zeta 1 is. I'll tell you more about that in a second. But we started by writing an innocent looking equation saying it's not innocent at all. Then we went and said, we got the solutions and we are saving 4 years of our life for every time we use a solution, to now saying, not only I got the solutions and I saved 4 years of my time, but I know that under many practical circumstances, this the whole solution becomes a simple formula of one term. Instead of being an infinite series, is one term. And now we save 4 years of our life and probably a couple hours, because calculating those series or programming them in MATLAB is a pain. But this, you will write this in quiz 3. You will do it, as they have done it in previous years. And you're doing so amazingly so far, I know it's going to go well. You're going to do, in a 2-hour quiz, the work of 4 years plus a day of calculation, because we managed to pack it so well here. Not my credit, credit of 300 years of heat transfer. But it gets better, Because if in addition of being long times, we say the Biot number now is very high, and we know if the Biot number is very low, trivial, go back to week 3 of classes and we do lumped capacitance. So let's go the other way, say, oh, no, Biot is not small, Biot is huge. If Biot is huge, right, but let's say by huge I mean more than 10, C1 is 4 over pi for a wall, done. You don't even need to start wondering what it is. Zeta 1 is pi over 2 for the wall. This implicit equation, this is a solution for the case of Biot tends to infinity. And the temperature on the surface becomes the temperature of the fluid. Same for the cylinder and same for a sphere. In the case of the sphere, C1 equals 2, and we're going to see that it plays a role. Zeta 1 is pi. And in all cases, the temperature of the surface is more or less the temperature of the fluid. Just think of this. You, with a bit of understanding of what the Biot number is and the Fourier number is, in many cases, you can give this result of a partial differential equation, which is an infinite series. You can reduce it to a very simple plug and chug business. No finite elements, no nothing. Actually, finite elements should match this. You use these formulas to compare, to see if your finite elements work. Okay, let's say Biot is not 0, so it's not lumped capacitance, but it's not infinite, so I cannot go to the easiest of all cases. How do I calculate this C1 and this Zeta 1? We need to solve an implicit equation. That's numerical. Like you would use in Excel, you would use the solver. Many of you have calculators that can do that type of stuff, solving for a term. And you would get the value of Zeta 1. But that's not the smart way of doing it, right? Because if it depends only on Biot, the book puts a table. I don't know why books for which you pay so much money and are made in the 21st century have these tables. They should. There is actually an alternative that I thought I had discovered myself. And when I was all excited about publishing it, I did a bit of literature review, and I didn't invent it myself. Somebody else invented it. Of all places, another professor in Canada. And this makes Canada a double awesome place. So is this. Zeta 1 can be thought of the combination of two cases. Zeta 1, 0, that is the value of Zeta 1 when the Biot number tends to 0, right? That would be the case of lumped capacitance. And Zeta 1 infinity, that is the value of Zeta 1 when Biot tends to infinity. So this Zeta 1 depends only on Biot. Biot can be as little as 0, as big as infinity. So this is called blending, and it's an extremely powerful tool that we use very much in our research that says, I can analyze simple cases by exaggerating things to be either 0 or infinity. And if you ask me, okay, how about something in the middle? I would say, wait a second, I can calculate whatever is in the middle as a combination of what is at 0 and at infinity. There is some sort of weighted average that would give you the values in the middle. And this weighted average is done with this formula, in which you get one number to the n plus the other extreme to the n, and both to the 1 over n. When you do this, right, the solution is not exact, but for this blessing of God, the solutions are within like a small percentage of the exact solution. And this is so much easier to calculate than using a numerical method or using Excel's solver or doing something in your calculator each time. So what is the value at infinity? I gave it to you already. Zeta 1 at infinity is either pi over 2 for the wall 2.405 for the solid cylinder or pi for the solid sphere. That's what you have for infinity. When we are near the lump capacitance case, zeta 1 is square root of B odd or square root of 2B odd or 3B odd, depending if it is the wall, the cylinder of the sphere. We put this inside this formula, and we use this n number. This n number is determined in a way that it minimizes the worst possible error, right? And this worst possible error is never bigger than something of the order small percentage. Now, we don't need to solve a partial differential equation. We don't need to do an infinite series. We don't even need to solve an implicit equation. If you're a physicist, you'd be solving the partial differential equation. You'll be doing the infinite series, and you'd be solving the implicit equation. And you'd be giving an answer years from now. And physicists don't make rockets. We engineers make rockets. So for that reason. How about an example? So we put all these, like, I'm telling you that things are so much simpler, but all you saw is infinite series. So some of you took me on faith, and some others perhaps not even that. Let's see an example. This is an example from the book. I think it's example 5.5. So my plan is to go through this example today, and on Monday to discuss the semi-infinite solid. So, but by the way, although this is an example of the book, I did consulting for a local company here in Alberta that had almost exactly this problem. It was not a pipeline with hot oil. It was a company making polymers, and a relief valve would open up when the polymer mix was too hot, and would blow like an extremely hot flow of these polymer and gases, and the pipe would be so hot that would have phase transformations and would end up with martensite and all kind of things that our MATI people would know. Consulting was this formula. So let's do it. So this is from the book. It says a pipeline made out of steel is 1 meter in diameter, has a wall thickness of 4 centimeters, is insulated on the outside, and is all at the same temperature. Here it says minus 20 C, and when flow has a flow of hot oil going at 60 degrees C, right? And it has a convection coefficient inside the pipe that is 500 watts per meter square Kelvin. Here we have the properties of steel, and let's solve one step at a time. This is problem 5.5 in the book. What are the Biot and Fourier numbers after 8 minutes after the initiation of the flow? So let's see what happens 8 minutes after. Oh, here we have a schematic, right? Here we have the pipe. The insulation is outside. Some of you asked me during the quiz on Monday if the insulation of the pipe would be inside, right? Of course not, because the insulation, the pipe is containing a fluid, and the insulation is protecting the heat transfer. But if we were to insulate the pipe inside, we would need another pipe to protect it from the fluid, like leaking into the insulation, right? So here we have a pipe. Here outside we have the insulation. Inside we have the hot flow of oil. And let's see. Biot number is HL over K, right? And H we know was 500 watts per meter square Kelvin. L is the thickness of the wall in this case, right? And over K, and K is the thermal conductivity of the wall. Before I go too far, let's do something. Something I didn't like of the problem, the way that it's set up in the book, is that something I didn't like of what the book is that they make many simplifications without telling you. So they have this pipe, right? And you would first think that because a pipe is cylindrical, we would be using the equations for a cylinder. But that's not the case. So that is a little bit misleading, because equations for a cylinder that we have are the equations for a solid cylinder, not a hollow cylinder. So that equation cannot be. The equation we're going to be using is the equation of a plane wall, because if the pipe has 1 meter in diameter, but a 4 centimeter wall, the wall is so thin that essentially believes that the wall has no curvature, right? So this is a simplification that requires quite a bit of maturity. In the book, they go through it without telling you much, as if it is obvious. But I'm telling you, so we're going to be using the equation of the plane wall because the wall is very thin compared to the diameter of the cylinder. If this was a problem of thermal resistance, we would know that the error was thickness over diameter. So 4 centimeters over 1 meter is of the order of 4% error. I'll take it. You don't know thermal conductivity with that accuracy. So that's one thing. Here's another thing that the book does without telling you, but it's very important. Let's see our wall here. Here we have a wall that has convection inside and convection outside. And because the wall is symmetric, we would have an axis of symmetry. And they consider that the wall has a thickness of 2L, or better said, 1L one direction and 1L the other direction. So the wall has a thickness of 2L in this case, and has convection on both sides. Here, in the pipe, not only we're assuming it is a wall, which it isn't, but we're going to call it a wall and not fuss much about it. But in addition, the wall has a thickness of L, not 2L. What happened here? What happens is the wall is insulated outside. Remember, the book said, the problem statement said that the pipe is insulated outside. If the surface is insulated outside, this is an adiabat. This line is an adiabat. Same as a line of symmetry. So this wall that is convection on one side, has convection on one side, and insulation is the exact equivalent of this other wall that has convection on both sides. Why? And we did discuss this last class. In the axis of symmetry, we have no heat transfer. If we were to look, for example, at the temperature profiles, the slope in the center is always 0. And if the slope is 0, heat transfer by conduction, right, that is proportional to the slope, is 0 because it's proportional to a 0 slope. I had many steps of reasoning here. My hope is that they become kind of automatic to you. So symmetry means a flat profile in the center, which means no gradient, which means no heat by conduction, which means this is the same as being insulated, the same as being insulated, like in this case. So you see, the most difficult part of the problem is not the math. It's just thinking how the reality can match one of our ideal models. Our reality is an insulated pipe. Our ideal model is that of a plane wall, right? And the insulation is the same as an axis of symmetry. An insulated pipe and a normal wall don't look at all the same. But from the point of heat transfer, they are the same. That's why we're taking this class, because these things are not intuitive. Anybody would say, this is a wall, that is a pipe. And you would say, yeah, it's the same. But you can only say that because you took this class and you saw how you translate things from one to the other, even though your eyes don't see that. Your mind knows it. Okay, that was the most important part. That's the key of everything we have done. So now we can calculate the Biot number, HL over K, 0.3. This is the worst that can happen to you, right? If the Biot number was 10 to the minus 3, we go back to week 3 and you do lump capacitance and you laugh all the way to the bank. If the Biot number was 10 to the 3, you know pretty much everything about it, because the surface of the pipe is going to be the surface of the temperature at the temperature of the fluid, and we have the coefficients already there. This problem hit us just where it hurts, right more or less 1, where you cannot say this is one extreme or the other extreme, but this is on purpose, right? So this is the Biot number. So we know it's not too small and not too big. It's kind of a Goldilocks thing, and in this case, Goldilocks is bad for us. But Fourier number, where do we do Fourier number? Okay, here. Fourier number is alpha t over L squared. We plug and chug was 8 minutes and is 5.65. Now we got one good news. It's more than 0.2. Actually, it's a lot more than 0.2. This means if we're bigger than 0.2, this means that the infinite series is just good to talk about, because we're going to use only the first term. We're going to take that one seriously, but only that one. Life is so much better. We're going to see on Monday that actually if Fourier is less than 0.2, there is another easy alternative to the problem. The bottom line is, every time things get too complex, there is a cheat around them that is going to help us. So, because the Fourier number is bigger than, we know we are not going to be doing lump capacitance, so we're stuck with the formulas we learned on Monday and today. Because we know Fourier number is bigger than 0.2, we're going to take only the first term. For the case of the wall, this was the formula. This formula is the one that we had in the table before. So in this formula, we need to know C1 and zeta 1. Okay, for that, we use this blending technique we have discussed. We have to start with zeta 1. And zeta 1 was a combination of zeta 1 at Biot 0 and zeta 1 at Biot infinity. What is zeta 1 at Biot 0? Was the square root of Biot. And that comes from this table we have here for the wall. Right? And here you see the formula. Okay. Are we good? Okay. This. And we calculated square root of 0.559. Then the other part of the combination was zeta 1 at infinity. That is pi over 2, again, from the same table. And we know it because what came from that table again. And when we do this blending, we end up with this conclusion that zeta 1, for this intermediate case, that is the worst that could happen, is 0.533. Whatever it is, 0.533, but now I put it inside the formula for C1, and we get this 1.047. Whatever it is, it's plug and chug. These numbers, I'm sure they make a lot of sense to the experts on plane walls, but for us at this stage, they're just numbers. They don't have a particular physical meaning right now. We put them inside the equation and we get a value of theta star, 0.214. Again, these numbers, which are dimensionless, make little intuitive sense for us right now. When you're an expert, they talk to you. I don't expect that at this stage. Right? Just let's plug and get an answer. Now, the question is, what is the temperature on the surface after 8 minutes? What is the temperature on the surface of the pipe, not on the outer surface of the pipe, right? 0 is at the center after 8 minutes. Okay, so would be if I unpack, right, this expression, this is the formula for theta. So from this formula, I can solve for temperature. This is initial temperature, temperature of the fluid here. So I'm going to solve for the T of xt, right? And we have it here. Do we? Here. And so we have T infinity plus blah, 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 all these, and it's theta of 0, 5.64. The outer surface of the pipe is at x equals 0, so cosine of 0 goes away, and will be C1 exponential of this, of theta 1 squared t. Only this part is the one that matters. We calculate the value here, right? Cosine of 0, and get 0.214. Put all this in the formula, and now we got a real number. We got a number of 42.9 degrees C. The outer wall of the pipe, the one that is in contact with the insulation, after 8 minutes is going to be at 42.9 degrees C, right? We arrived to this first by thinking a little bit intuitively, right? By knowing that whether it's lamp capacitance or not, whether the fluid is very intense or not, the cooling of the convection of the fluid is very intense or not. But after those first grasps, we follow a systematic procedure, replacing the formula, the values in the formulas, until we got to a temperature. And this is a temperature that could only have been obtained after somebody doing 4 years of a PhD to solve this equation. So we're 4 years wiser today just for having done this. Another question we have, please, you have this in the notes and you have it in the book, so please go over this. And another question we have is, what would be the heat flux into the wall? There are 2 ways of calculating this. Heat flux can be calculated using Fourier's equation, well, put into the wall. In reality, it would be into the pipe. We could use Fourier's equation, and from the gradient of temperature, calculate a heat flux. Or we can be smarter than that and know that the heat coming into the pipe from the fluid comes by convection. And convection, I know how to calculate, is H times T of the fluid minus surface temperature. T of the fluid I know, H I know. I don't know the surface temperature, but I have the formulas to calculate the surface temperature. And I use those formulas again. Now, X star, instead of being 0, as it was before, for the outer wall of the pipe, was the center of symmetry. That is where the coordinate was based. And so in these formulas. So now instead of being 0, X star is going to be 1. That is the surface of the wall. So you see, we plug all the things that look much as before, but we have cosine of something that is not 0 anymore, is 0.533 times 1, not times 0. We get this value, whatever it is, because it's a dimensionless value, but we got it. We put it into the formula for temperature, that is just this, that comes from this formula that turned temperature into a dimensionless magnitude. And we got TS, and says that T at the surface of the pipe, the inner surface of the pipe, right, would be 45 and something degrees C, right? And so we can finally calculate the flux. We have this inner temperature, and we have a straight answer. I do something in my notes that is not in the book, but it's cool. Look, the pipe, in the inner surface of the pipe is 45 degrees C, but the outer surface of the pipe, we calculated before, was 43 degrees C. It's not that different. So the Biot number is 0.3. It's not 0.1. So it's not really lumped capacitance, but it's not too far from lumped capacitance. So let's compare, let's do lumped capacitance and see how it compares for this problem in particular, right? If we had done lumped capacitance. You already know how to do this because you did it in quiz 1 and you did it very well. And if we could rewrite the formulas from lumped capacitance. Here we have it, this equation 35. We could rewrite it as this other way using the concept of Biot and Fourier. Same thing, no simplification, it's just a rewrite in the context of the things we have learned recently. And what does it say? It says that if we had considered lumped capacitance, we would say that the outer wall, the outer surface of the pipe and the inner surface of the pipe would be at the same temperature. Of course, it's lumped capacitance. But that temperature would be 45 degrees, would be 46 degrees C. Right? Not too bad. Wouldn't have been too bad. So we did it the right way first. Then we cut a few more corners by doing lumped capacitance, and we could compare those two, right? The whole problem here was about trying to, the whole problem here was the mechanics to use these formulas for transient conduction. One other thing that is interesting, here we have the formula to estimate the temperature gradients inside the pipe, inside the wall, right? And says Biot over 2, and this is what we saw on Monday. And if I replace numbers, I would get that my estimation of temperature gradients in the pipe wall would be 2.31 degrees C. This factor of 2, I told you, came because it's more or less 2. And I knew, actually, this is part of my PhD thesis, getting things like this number 2. Let's now do the proper math. 4 years of a PhD later, we come to the exact equations, and the exact equation said that inside is at, the pipe inside is at 45 degrees, outside is shy of 42 degrees, and the temperature gradient inside the wall is 2.35 degrees C. Look, 4 years of PhD versus a simple formula, right? This formula is based on lumped capacitance. It's not exact, but in this case, our estimate of the gradients was pretty good, right? And if we go all the way with lumped capacitance, our estimate of pipe temperature is not that bad. We're gonna stop here. We will wrap transient conduction on Monday. I wanted to wrap it up today, but I saw we were a day behind. And then we're going to start working, discussing convection and boundary layers. Let's stop here. I'll take a 10-minute break and come back at 2 for office hours. Thank you, everybody, and until later.